Hello. Today we're going to talk about sequences of functions. First, let's review the properties of nowhere differentiable functions. Last time, we found that there are functions which are everywhere continuous and nowhere continuous. For example, we found that every polynomial is a continuous function. We also found, by an example of Peter Lejeune Dirichlet from 1829, that there is a function which is discontinuous everywhere. Consider that function f that takes on the value 1 whenever x is a rational number and 0 whenever x is irrational number. We also found that there are functions which are everywhere differentiable. For example, polynomials are everywhere differentiable. And we found that differentiability implies continuity. That is, let I be a closed interval. If f is a function on this closed interval which is differentiable at a point P, then f is continuous at this same point P. This leads into a couple of motivating questions. Can we find a function which is continuous but not differentiable? Can we find a function which is nowhere differentiable? This question was originally asked by Carl Weierstrass back in 1872. He found the following answer. Fix two real numbers a and b satisfying the following three properties. First, a is between 0 and 1. Second, b is a positive odd integer, such as 1, 3, 5, 7, and so forth. And third, the product of a and b is greater than 1 plus 3/2 pi. He showed that the following function, which can be expressed as an infinite sum, is well-defined, continuous everywhere, but differentiable nowhere. As a quick remark, about 40 years later, the English mathematician Gottfried Hardy proved that the conditions can be relaxed a little bit. You only really need to have a is between 0 and 1, and the product a times b is greater than 1. So now this leads to another couple of motivating questions. First, why is this function well defined? What does it mean to take an infinite sum? Before we get there, we state a couple more properties about this function. There exists a constant m and a constant alpha, such that in absolute value, f of x minus f of p is less than or equal to m times x minus p to the alpha for all real numbers x and p. If the same property is true for any other function on a closed interval I, we say that this function is Holder continuous. That is, say that we have a well-defined function f on a closed interval I from a to b, such that there exists constants m and alpha, such that f of x minus f of p is less than m times x minus p to the alpha for all x and p in I. We have a few properties about Holder continuous functions. Again, say that I is a closed interval and f is a well-defined function on I. F is Holder continuous for alpha equals 1 if and only if it is a Lipschitz function. F is Holder continuous for alpha greater than 1 if and only if it is a constant. And third, if f is Holder continuous, then f is uniformly continuous. In particular, every Holder continuous function is a continuous function. To continue along the lines of our motivating questions, let's consider a series of motivating examples. Previously, we defined a function, f of x, as a limit as n increases without bound of a sequence f sub n of x, where f sub n is a sum 1 plus alpha times cosine of beta pi x plus alpha squared times cosine of beta squared pi x, and so forth. More generally, we can say let I be a closed interval, and let's consider a sequence of functions f sub 1 of x, f sub 2 of x, f sub n of x, and so forth that are defined on this closed interval I. First, what is the definition of saying f of x is the limit as n increases without bound of f sub n of x? Second, when is f a continuous function? And finally, when is f a differentiable function? Let's consider several examples to gain some intuition before we jump into the answers to these motivating questions. For our first example, let's consider a sequence f sub n of functions defined on the entire real line coming from polynomials of degree 2. That is, f sub n of x will be the ratio x squared plus nx divided by n. Here on your screen, you can see various plots of this function f sub n of x. When n is equal to 1, we have the polynomial x plus x squared. When n is equal to 2, we have the polynomial x plus 1 half x squared, and so forth. You can see here that it appears that these plots of functions are somehow flattening out and that they become a straight line. In fact, if we observe that as n increases without bound, the coefficient 1 over n tends to 0. So x squared over n tends to 0 as n increases without bound for any fixed real number x. This means that we can write our function f of x, which we think of as the limit as n increases without bound of f sub n of x, just to be the linear function x. Here's a key observation. Although each function f sub n is a quadratic polynomial, its limit is a linear polynomial. Let's consider a second example. Now consider a sequence of functions f sub n defined on the entire real line that are polynomials of degree n minus 1. That is, f sub n of x is 1 plus x squared plus x to the n minus 1. Again, you can see plots of the various examples. For example, when n is equal to 1, we just have the constant f sub 1 of x equals 1. When n is equal to 2, we have the linear function f sub 2 of x equals 1 plus x. You can see that it appears in some way that these functions are perhaps flattening out a little bit, but actually the right thing to say is as follows. When the absolute value of x is less than 1, the absolute value of x to the n tends to 0 as n increases without bound. This means that we can write our function f of x, which is the limit as n increases without bound of the f sub n of x, as the rational function 1 over 1 minus x. Again, this will make as our definition when x is between minus 1 and 1. Here's a key observation. Although each function f sub n is continuous for all real numbers, the limit x is only defined on the open interval from minus 1 to 1. Let's consider another example. Consider the sequence of functions f sub n defined on the entire real line, where f sub n of x is equal to x to the n. Here are some examples of the plots. When n is equal to 1, we have the linear function f sub 1 of x equals x. When n is equal to 2, we have the quadratic function f sub 2 of x equals x squared. We see that when the absolute value of x is less than 1, the absolute value of x to n tends to 0 as n increases without bound. However, when x equals 1, we see that 1 to the n equals 1. This means that we can make the following definition of our function f of x, which is the limit as n increases without bound of f sub n of x. F of x equals 0 when x is between minus 1 and 1, whereas f of x equals 1 when x equals 1. Here's the key observation. Although each function f sub n defined on the real numbers is continuous, the limit defined on the closed interval from minus 1 to 1 is discontinuous. And here's our final example. Let's consider a sequence f sub n of functions f sub n defined on the real line, where f sub n of x equals x to the 2n divided by 2n minus 1. We can think of this as follows. Let's take x squared and raise it to the following rational number, n over 2n minus 1. We note that each of these functions f sub n is actually differentiable. We can take a look at the plots here. When n is equal to 1, we see that we just have the function f sub 1 of x equals x squared. When n is equal to 2, we see that we have the function f sub 2 of x equals x squared raised to the 2/3 power. As we increase n, we we see that we actually do have functions that start out as a quadratic parabola and they somehow flatten out to a V shape. This means, by considering the plots that you see, that f of x, which is the limit as n increases without bound of f sub n of x, is just the absolute value of x. Here's the key observation. Although each f sub n is differentiable for all real numbers, the limit is continuous for all real numbers, but not differentiable. This leads into the topics for today, that is, sequences of functions. Let's start with some key definitions. Let I be a closed interval, and let's consider a sequence f sub n of functions fn going from the closed interval I to the real numbers r. We'll say that this sequence converges pointwise to a function f, also defined in the closed interval I, if the sequence a sub n, defined by a sub n equals f sub n of p, converges to a limit f of p of the a sub n. We give another way to view this. Fix an element p of our closed interval I. Given a positive epsilon, there should exist a delta such that in absolute value, f sub n of p minus f of p is less than epsilon whenever n is greater than delta. We'll say that this sequence converges uniformly to a function f if, given a positive epsilon, there exists a delta such that in absolute value, f sub n of p minus f of p is less than epsilon whenever n is greater than delta and p is an element of our closed interval. The difference between converges pointwise and uniformly convergent is converges pointwise depends on a specific point p. That is, delta will depend upon p. Uniformly convergent does not depend upon p. That is, the delta should be independent of the choice of p. In either case, we will say that f equals the limit as n increases without bound of f sub n, or this function's f sub n tend to the function f. Before we continue, let's discuss a few examples. Let's consider the functions f sub n and f defined on the real numbers as follows. F sub n will be x plus 1 over n x squared, and f of x will just be x. We're going to show that f sub n tends to f pointwise. Let's fix the point p in the real numbers. Given a positive epsilon, let's choose delta to be p squared over epsilon. Then it's not hard to show that in absolute value, f sub n of p minus f of p is less than epsilon whenever n is greater than delta. Here's another example. Let's consider the open interval I from -1 to 1 and consider the two functions f sub n and f defined as follows. F sub n will be the sum of the first powers of x, namely 1 plus x to the n minus 1, and f of x will be 1 over 1 minus x. Again, we'll show that f sub n tends to f pointwise. Fix a real number p. Given a positive epsilon, we can choose delta to be the log of 1 minus absolute value of p times epsilon divided by the log of the absolute value of p. To be precise, we have to be a little bit careful when p is equal to 0, but we'll ignore this for now. Then, in absolute value, f sub n of p minus f of p is less than epsilon whenever n is greater than delta. And here's our final example. Let's consider I to be the open interval from 0 to 1 and consider the functions f sub n and f to be defined as follows. F sub n of x is x to the n, and f of x is 0. Again, we'll show that f sub n tends to f pointwise. Fix a real number p. Given a positive epsilon, we'll define delta to be the log of epsilon divided by the log of the absolute value of p. Just like before, we have to be a little bit careful when p is equal to 0, but we'll ignore this for the moment. Then, in absolute value, f sub n of p minus f of p is less than epsilon whenever n is greater than delta. We have this concept of being a uniformly convergent sequence of functions. We relate this to the concept of the Cauchy criterion that we've seen before. Let I be a closed interval, And let's consider a sequence f sub n of functions defined on I. Then this sequence is uniformly convergent if and only if, given a positive epsilon, we can find a delta such that f sub m of p minus f sub n of p is less than epsilon whenever m and n are greater than delta and p is in the closed interval I. We'll discuss the proof. Let's fix a positive epsilon. First, let's assume that our sequence is uniformly convergent where the limit is a function f. Then we can find a delta such that f sub n of p minus f of p is less than epsilon over 2 whenever n is greater than delta and p is an element of our closed interval. Hence, if we consider f sub m of p minus f sub n of p, we can use the triangle inequality to write this in terms of f sub m of p minus f of p plus f sub n of p minus f of p. This, of course, is less than epsilon over 2 plus epsilon over 2, which is epsilon. Now let's consider the converse direction. Assume that we can find a delta such that f sub m of p minus f sub n of p is less than epsilon whenever m and n are greater than delta, and p is in our closed interval. For the moment, let's fix p to be in our closed interval, and let's consider a sequence a sub n equals f sub n of p. This, by our assumption, is a Cauchy sequence, so there exists a limit L. Let's define our function f from the closed interval to the real numbers by writing f of p equals this limit L. It suffices to show that our sequence converges to f uniformly. Given a natural number k, we can find an m greater than delta, where m possibly depends upon p as well as k, such that the absolute value of f of m of p minus f of p is less than epsilon divided by 2 to the k. Now, for any n greater than delta, we have f sub n of p minus f of p, by the triangle inequality again, is less than or equal to f sub m of p minus f sub n of p plus f sub m of p minus f of p. But this is less than, parentheses, 1 plus 1 over 2 to the k, parentheses, times epsilon. The point now is that the left-hand side and the right-hand side are independent of m. Similarly, the right-hand side really says that our k was arbitrary, so we can let k be anything. In fact, if we let k increase without bound, we see then that the absolute value of f sub n of p minus f of p is less than epsilon whenever n isn't greater than delta and p is in our closed interval. But this is exactly what it means to say that our sequence converges uniformly. Next, we'll state one of our big 3 theorems for today. Let I be an open interval and say that we have a uniformly convergent sequence of continuous functions f sub n. And we'll show that the limit f is also a continuous function. And what we'll say for the proof, let's fix p to be in our open interval and say that epsilon positive is given. First, since the f sub n's form a uniformly convergent sequence, we can find a capital N such that in absolute value, f sub n of x minus f of x is less than epsilon over 3 whenever n is greater than capital N and x is in our open interval. Now let's fix an n0 greater than capital N. Since we have a sequence of continuous functions, we know that there exists a delta such that f sub n0 of x minus f sub n0 of p is less than epsilon over 3 whenever x minus p is less than delta. Now, whenever x minus p is less than delta, we can consider the absolute value of f of x minus f of p. Using the triangle inequality, we see that this is less than or equal to the absolute value of f sub n0 of x minus f of x plus the absolute value of f sub n0 of x minus f sub n0 of p plus the absolute value of f sub n0 of p minus f of p. But these are each less than epsilon over 3, so their sum equals epsilon. By the epsilon delta criterion, we then see that our limit f must be a continuous function. Next, let's discuss the uniformly continuous limit theorem. Just like before, let I be an open interval, and let's consider a sequence of uniformly continuous functions f sub n, and we'll assume that our sequence is a uniformly convergent sequence. Then the limit f is also a uniformly continuous function, and in particular, for every point p in our open interval, we have the limit as n increases without bound of the limit as x tends to p of f sub n of x equals the limit as x tends to p of the limit as n increases without bound of f sub n of x. In other words, we can interchange the limits. Let's say that a positive epsilon is given. Since our sequence of functions f sub n is a uniformly convergent sequence, we can find a capital N such that, in absolute value, f sub n of x minus f of x is less than epsilon over 3 whenever n is greater than capital N and x is in our open interval. Now, let's fix an n0 greater than capital N. Since each of the functions in our sequence is uniformly continuous, there exists a delta such that, in absolute value, f sub n0 of x minus f sub n0 of p is less than epsilon over 3 whenever x minus p is less than delta. You'll notice here the difference in this part of the proof versus the previous part is that our delta is independent of the point p. Now, whenever x minus p is less than delta, we essentially use the same argument as before to show that f of x minus f of p is less than epsilon, and of course here the delta is independent of p. By the epsilon delta criterion, we see that our limit must be a uniformly continuous function. Since a uniformly continuous function is actually a continuous function, we now see that the limit as n increases without bound of the limit of x tends to p of f sub n of x is just the limit as n increases without bound of f sub n of p. But by definition, this is equal to f of p because f is the limit of our sequence. Now f is a continuous function, so this is equal to the limit as x tends to p of f of x. But now f is the limit of this sequence, so this is equal to the limit as x tends to p of the limit as n increases without bound of f sub n of x. Finally, let's discuss the differentiable limit theorem. Let I be a closed interval. Let's assume that the f sub n's forms a convergent sequence of differentiable functions, and the derivatives fn prime forms a uniformly convergent sequence. Then the limit f is also a differentiable function, and its derivative is the limit of the fn primes. Let's discuss the proof. Denote g as the limit of the fn primes. We're going to show that our limit f has derivative f prime, which is g. To this end, let's fix the point p in our closed interval and say that a positive epsilon is given. We need to discuss 3 inequalities. First, using the mean value theorem for the difference f sub m of p minus f sub m minus f sub n, and invoking the Cauchy criterion for the uniformly convergent sequence fn prime, we can then find an n sub 1 such that we have here the absolute value of the difference of differences. That is the absolute value of f sub m of x minus f sub m of p divided by x minus p minus f sub n of x minus f sub n of p over x minus p. This should be equal to the absolute value of fm prime of q minus fn prime of q for some q between x and p. Again, this is the mean value theorem. This now is less than epsilon over 3 for any m and n greater than n sub 1 and any x not equal to p by the Cauchy criterion for our uniformly convergent sequence fn prime. Now, as m increases without bound, we really say that this inequality here is completely independent of m. So we can say that the absolute value of f of x minus f of p over x minus p minus f sub n of x minus f sub n of p over x minus p is less than epsilon over 3. As a caveat, this isn't quite a rigorous proof, but one can make the proof of this inequality rigorous by using the ideas that we explained before in our proof of the Cauchy criterion for uniform convergence. Still, this is the first of our 3 inequalities. Next, since our sequence fn prime is uniformly convergent, we can find another number n sub 2 such that gn prime of x minus g of x is less than epsilon over 3 whenever n is greater than capital N2 and x is in our interval I. Third, let's fix an n0 that's greater than n1 and greater than n2. Since our sequence of f sub n's is differentiable, there exists a delta such that the absolute value of f sub n0 of x minus f sub n0 of p over x minus p minus f n0 prime of p is less than epsilon over 3 whenever x minus p is not equal to 0, but less than delta. Putting these 3 together, we then see that the absolute value of f of x minus f of p over x minus p minus g of p, we can write using the triangle inequality in terms of the 3 inequalities we've just discussed. But since each of these inequalities is less than epsilon over 3, the sum of the 3 of them will be equal to epsilon. But this now shows that our limit f really is differentiable and its derivative, f prime, is equal to g. Thanks very much for watching.